The universe's biggest discoveries often start with a mistake, just a simple error. I'm going to talk about 30 of those accidents, 30 times something went wrong in astronomy, and it changed everything. By the time we're done, the whole history of looking up at the sky is going to feel different. There was a hidden planet found because a lens was broken. There was this hiss of static, just frustrating noise, and it turned out to be the echo of the beginning of everything. We'll get into stories about telescopes that were pointed wrong, about data that got forgotten, about lucky mistakes. They showed us the deepest secrets out there. Every story says the same thing. The biggest truths usually show up when we wander off the path. Makes you wonder what we'll find the next time we slip up. An astronomer was mapping radio waves from distant stars. He was trying to trace the shape of our galaxy, but his equipment kept picking up this hiss. A constant background noise. It was ruining his measurements. He checked everything. He even thought it might be pigeon droppings in the antenna, but the hiss was still there. That frustration, that thing he couldn't get rid of, was the cosmic microwave background radiation. He wasn't looking for the echo of the Big Bang. He was just trying to clean up his data. And he found the oldest light in the universe. That's serendipity in science. It's not just blind luck. It's when a curious mind, a prepared mind, runs into something completely unexpected. Louis Pasteur said it, chance favors the prepared mind. In astronomy, that preparation means building instruments sensitive enough to hear the universe whisper. And then having the humility to listen when it says something you didn't ask for. The cosmos is full of things we haven't even thought to look for. So when a telescope glitches, when a photograph has a strange smear, when a computer model gives you a number that makes no sense, that isn't always a failure. Often, it's the universe tapping you on the shoulder. It's pointing to a door you didn't know was there. These stories are about those taps, those moments of confusion that turned into clarity. Our greatest discoveries so often start with a simple mistake. A beautiful mistake. That faint disk didn't twinkle. It wasn't like any star. William Herschel was at his telescope, a cold night in March 1781. He'd built the instrument himself. His project was to catalog double stars. He was sweeping the sky, and his lens passed over this small, steady glow. Stars twinkle, planets don't. That was the first clue. Herschel was a musician, an astronomer by passion. He recorded it as a comet, but the path was wrong. Comets have elongated orbits. This object moved slowly, a nearly circular path far beyond Saturn. The truth was clear. He'd found a new world. The discovery of Uranus was a shock. For millennia, the solar system was a known family. 6 planets, Saturn as the distant sentinel. That model was complete. Herschel's discovery tore that boundary down. Overnight, the known universe doubled. Here was a massive planet, 4 times wider than Earth. It had been gliding through the darkness for centuries. Seen but never recognized, astronomers had logged it before, at least 22 times, each time dismissed as a faint star. It took an amateur, a homemade telescope, no preconceptions, to finally see what was right there. This was the first great accidental discovery. Herschel wasn't looking for a planet. He was pursuing his own project. But he was meticulous. He noted every anomaly, and he stumbled into a revolution. His find announced a powerful idea. Our maps of the cosmos are never finished. Major pieces can hide in plain sight, waiting for someone to look at the familiar sky with fresh eyes, to ask a simple question. What is that? The universe had just gotten much bigger. Because of a musician who loved the stars. The discovery of Uranus showed us the universe was larger than we'd imagined, but the next big accident revealed it had a starting point. It began with a telephone company issue. Arno Penzias and Robert Wilson at Bell Labs in 1965. were trying to pick up faint radio signals from space. They had this giant horn antenna built for satellite communication, but their instrument wasn't working right. It kept picking up a constant hiss, a low, steady static that came from every direction in the sky. And it wouldn't stop. They checked every wire, every connection. They thought it might be interference from New York City. It wasn't that. They even found a pair of pigeons had nested inside the horn. They cleaned out the droppings, shooed the birds away, sealed the antenna. The hiss was still there. This wasn't a signal. It was noise, and for two frustrated engineers, it was the enemy of their work. They couldn't eliminate it. They were about to write it off as some strange, unexplained flaw in the equipment. Just a few miles away, a team of physicists at Princeton was building a very different instrument. They weren't fixing a problem, they were hunting for a ghost. Robert Dicke and his colleagues had a theory. If the universe started in a hot, dense state, a big bang, it would have left behind a faint, cool glow. Radiation stretched by the expansion of space over billions of years into the microwave part of the spectrum. It would be everywhere, a uniform bath of energy filling the cosmos. They were building a detector to find it. When Penzias heard about this search, he made a phone call. A simple question passed between the engineer and the theorist. What if my problem is your answer? That persistent hiss, that omnidirectional static, matched the Princeton prediction exactly. It wasn't broken equipment. It was the echo of creation, the cosmic microwave background radiation, the cooled remnant of the universe's first light. In that moment, cosmology changed. What was speculation became hard science. The Big Bang Theory had its smoking gun. Two men trying to fix an antenna had accidentally tuned into the oldest broadcast there is. The faint whisper of the universe's infancy. It tells us that everywhere we look, in every empty patch of sky, we are surrounded by the afterglow of the beginning. There was this constant hiss, a cosmic whisper, but then, a few years later, a graduate student at Cambridge heard something else, a ticking. 1967. Jocelyn Bell Burnell was looking at data from a new radio telescope. Miles of wire and poles built to watch quasars flicker. Her job was to go through these long paper charts from the telescope, and one day she saw a little squiggle. Just a bit of scruff on the line. It wasn't much, but it was odd, and it kept showing up in the same part of the sky. She marked it, checked the next charts, and it was there again. This time she could see a pattern. It wasn't random, it was a pulse, a perfect rhythmic beep, 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 every 1.337 seconds. So precise it seemed artificial, like a metronome. The team was baffled. They ruled out everything on Earth, not an airplane, not a satellite, not radar. The pulses kept coming. That regularity was almost unnerving. As a joke, they called the source LGM-1, Little Green Men 1. It was a way to handle the tension. The idea they'd found a beacon, a signal, the possibility sent a thrill through them, but Jocelyn kept working. She found more of these pulsing sources. Different rhythms, different skies. They couldn't all be lighthouses from other civilizations. The truth had to be natural, but extraordinary. The answer came from theory. From the death of massive stars, when a giant star explodes, its core can collapse into this unimaginably dense ball of neutrons, a city-sized object with the mass of a star. A neutron star, theorists said these spinning cinders could act like lighthouses. With a strong magnetic field, they'd beam radiation from their poles. And if that beam swept across Earth as the star spun, we'd see a flash, a pulse. That's what Jocelyn had found, not little green men, pulsars. The discovery was monumental. It confirmed neutron stars, matter crushed to its limit. It gave astronomers a new tool, a precise tool for extreme physics, and it started with a graduate student who didn't dismiss a tiny anomaly on a paper chart. She saw the scruff, and she chose to look closer. In that choice, she opened a window into the final moments of a star's life. revealing a clockwork heart ticking in the deep, a clockwork heart ticking somewhere in the dark, then a scream. That's what came next. A flash of energy so violent it could have erased our planet from light years away. And we found it because we were looking for bombs. The 60s were tense. The Cold War was everywhere. There was a treaty banning nuclear tests in the atmosphere. But how do you trust a signature? So the United States launched the Vela satellites, silent watchers in the void. Their only job was to look for the double flash of a nuclear blast. The first pulse of light, then the burst of gamma rays. They were built for suspicion, and in 1967 they saw something. A flash, but it was wrong. It came from deep space, not from Earth. And there was no first pulse, just a sudden, immense spike of gamma radiation. Then it was gone. The data confused the small team that could see it. This wasn't a Soviet test. The direction was all wrong. Over the next few years, the satellites kept catching these ghosts, brief, terrifyingly powerful bursts with no explanation. The findings were stamped top secret, locked away in a vault. For years, astronomers didn't even know these things existed. The universe had a secret, and our spy satellites had overheard it. It wasn't until 1973, when the data was declassified, that the truth started to come out. The astronomy community got this cosmic puzzle. These gamma-ray bursts were the brightest events we know of in the universe. In just seconds, they could release more energy than our sun will in 10 billion years. But what were they? The theories were wild. Comets falling into neutron stars. Alien ships exploding. The truth, once we pieced it together, was almost as staggering. Most bursts we know now are the birth cries of black holes. They come from the catastrophic collapse of a massive star's core, or the violent merger of two neutron stars, events that forge the heaviest elements. Like gold and platinum, we went from watching for the end of our world to seeing the violent beginnings of others. Instruments built for paranoia accidentally opened a window onto the most energetic engines in creation. It's a reminder, sometimes to see the universe's greatest spectacles, you have to be pointed in the right direction for all the wrong reasons. That terrifying flash of energy was kept secret for years. But there was another invisible force being mapped at the same time, and it was found because a counter on a satellite just stopped. 1958. The United States launched its first satellite, Explorer 1. It was a simple mission, a proof of concept to show America could get something into orbit. On board was a small Geiger counter built by a physicist named James Van Allen. Its job was to measure cosmic rays, those high-energy particles from the sun and deep space. The data came back as a steady stream of clicks. Then, at a certain altitude, the readings did something strange. They dropped to zero. The instrument went silent. A lesser team might have logged a malfunction, a broken sensor, but Van Allen and his students looked at that flat line and saw a puzzle. Why would a cosmic ray counter stop counting? Their insight was to flip the problem. What if the instrument wasn't broken? What if it was overwhelmed? They reasoned the counter might be so flooded with radiation it couldn't process individual particles. It was saturated, blinded by an intensity they hadn't predicted. That zero wasn't an absence, it was a signal of something immense. Later missions confirmed it. Explorer 1 had stumbled into a vast, donut-shaped shroud of charged particles, trapped by Earth's magnetic field, the Van Allen radiation belts. Two zones of intense radiation that encircle our planet, invisible but a critical part of our space environment. The discovery was accidental, but its implications were profound. It showed our planet isn't just a rock in space. It's a magnet, actively shaping and holding a dangerous, energetic environment around itself. This invisible shield and trap became a fundamental fact of space travel. Astronauts had to plan their paths through it. Satellites needed shielding. Years later, the same principle solved another mystery. When the Pioneer 10 probe flew past Jupiter in the early 70s, its radiation detectors went haywire. They pegged off the charts. Scientists realized they were seeing the same phenomenon, but magnified. Jupiter's magnetic field is thousands of times stronger than Earth's. Its radiation belts are a maelstrom of energy, so intense they'd fry unshielded electronics in minutes. A simple Geiger counter on a basic satellite, built for one job, ended up mapping the invisible architecture of worlds. It taught us to listen to silence, to understand that when an instrument seems to fail, it might just be whispering a truth too loud for it to hear. Asaph Hall was ready to quit. He'd been at the eyepiece of the 26-inch refractor at the Naval Observatory. This was in 1877. The telescope was good, but not the best. And what he was trying to do seemed impossible. Most astronomers thought Mars had no moons. William Herschel had looked and found nothing. A French scientist had declared it settled. Mars was moonless. But Hall heard that. He was stubborn. It lit something in him. He had to look for himself. So night after night, he'd point the scope at Mars, that bright red dot. And he'd sweep the space around it, looking for any faint speck that might be moving. The work was grueling. The planet's own glare could hide a moon. For weeks he saw nothing, just empty sky and the feeling of failure. He decided to stop. He told his wife, Angelina, he was done. It was futile, but Angelina knew him. She saw his disappointment, and she saw his resolve. She told him to try one more night, just one. That was the nudge. He went back to the observatory. On August 11, 1877, Mars was in the sky. He started his sweep again, and then he saw it, a faint point like a star, but it wasn't still. It was moving fast. The next night he confirmed it, and soon he found a second one, even fainter. He'd done it. Mars had two moons. He named them Phobos and Deimos. Fear and panic. It was a triumph of perseverance. It confirmed an old idea from Kepler, who'd guessed Mars might have two moons based on a pattern. But more than that, it showed something. Even with imperfect tools, against everyone's opinion, a determined observer could change the map. Those two tiny dots spotted because a wife believed in one more night, they became the first destinations for our probes to Mars. They're the stepping stones, a personal grudge, a moment of near surrender, and one night of renewed effort that gave us two new worlds. It reminds you. Sometimes the biggest obstacle isn't the limits of the instrument. It's the moment you decide to walk away from the eyepiece. They were flying out to measure Uranus. This was in 1977. A team led by James Elliott using NASA Airborne Observatory, a jet with a telescope in it. Their target was a specific star. The plan was to watch Uranus pass in front of it, an occultation. From the timing of the star's disappearance and reappearance, they could get the planet's exact size, the atmosphere's temperature, a precise, planned experiment. They're watching their instruments. The star's light is steady. Then, just before the planet itself should have blocked the light, the signal dipped. Not just once, several times, a sequence of quick, symmetrical flickers. Then the main occultation happened, just as predicted. And after the star came out from behind the planet, the flickers happened again. The same pattern in reverse. Their first thought was that it had to be an error, a glitch in the photometer, something wrong with the aircraft window. But the pattern was too clean, too perfectly mirrored on either side of the planet. That symmetry meant it was real. It was something around Uranus. The only possible explanation was rings. Narrow, dark rings. The star's light had been blocked not just by the planet, but by these bands of material orbiting it. They had accidentally discovered the rings of Uranus. Before that, rings belonged to Saturn alone. They were seen as a rare, decorative feature. This observation changed that. It suggested rings might be a common part of a gas giant structure. They went up to measure a world's diameter and came down having mapped its hidden rings. It showed that even a careful plan could be upstaged by a surprise. The answer was in the margin of the data, in a flicker they didn't plan for. You just have to believe the flicker is real. The rings of Uranus were a stunning find. But there was another shadow already being measured. Fritz Zwicky saw numbers others missed. In the 1930s, he was looking at the Coma cluster, a swarm of galaxies millions of light years away. He used a simple physics principle, the virial theorem. In a stable system like a galaxy cluster held by gravity, kinetic energy and potential energy are balanced. You can weigh the cluster by watching how fast its galaxies move. The faster they zip around, the more mass must be there pulling them in. Zwicky did the math. He added up all the light from the galaxies. He estimated the mass that starlight represented. Then he compared it to the mass his velocity measurements demanded. The numbers didn't match, not even close. The gravitational mass was hundreds of times greater. The cluster behaved as if it had a colossal, invisible anchor. Something was there providing gravity but giving off no light. Zwicky called it Dunkel Materie, dark matter. His personality didn't help. He was famously abrasive. He called his colleagues spherical bastards. Bastards, he said, no matter which way you looked at them. That attitude meant his radical idea was easy to dismiss. For decades, astronomy largely ignored his conclusion. It seemed too outlandish, a ghost in the machine, but the discrepancy wouldn't go away. Decades later, in the 1970s, Vera Rubin studied the rotation of spiral galaxies. She found the same problem on a smaller scale. Stars at the edges of galaxies were orbiting just as fast as stars near the center. According to gravity, this meant most of the galaxy's mass wasn't in the bright center. It was spread out in a vast, invisible halo enveloping the entire galaxy. She had independently confirmed Zwicky's missing mass. This wasn't a fluke of one distant cluster. It was a universal feature. That accidental discovery from a velocity mismatch pointed to a fundamental truth. Most of the matter in the universe is not like the matter we know. It doesn't shine, it doesn't reflect, it doesn't interact with light at all. It simply exerts gravity. This dark matter forms the hidden skeleton of the cosmos. It shapes how galaxies form and how they cluster together. We still don't know what it's made of. It remains the great unseen architect. Its nature is one of the most profound mysteries in all of science. And it all started with a brilliant, difficult man who trusted the numbers, even when they pointed to a universe mostly made of shadow. People have always watched comets. They were seen as signs, as warnings in the sky. But there was this one detail, obvious to anyone who looked. The tail of a comet always points away from the sun. Every time, even when the comet is traveling away from the sun, its tail streams out in front, like it's being pushed by some kind of wind. It was a beautiful fact. A reliable fact, and for a long time that's all it was. Just something people saw. No one really asked what was doing the pushing. That changed in the 1950s. A German astrophysicist, Ludwig Biermann, he looked at those tails and saw a problem. He knew they were made of gas and dust pushed by something. Sunlight pressure could explain part of it. But not everything. The tails were too active, too structured. Biermann ran the numbers. He decided there had to be something else. A steady stream of particles, not just light coming from the sun. A constant solar breeze. He called it corpuscular radiation. It was a radical idea. The common view was that space was a true vacuum, empty, still. The thought of our star constantly breathing out a storm of charged particles seemed almost like poetry. But it was just a theory. His conclusion, just from watching the sweep of a comet's tail, was the first prediction of what we now call the solar wind. The technology had to catch up to the idea. In 1959, the Soviet Union's Luna 1 probe, on its way to the moon, it directly measured that stream of particles for the first time. Then a few years later, NASA Mariner 2 spacecraft heading to Venus, it confirmed everything in detail. The solar wind was real. a supersonic river of plasma flowing past Earth at 1,000,000 miles an hour. That discovery changed how we see the Sun and the planets. This wind isn't gentle. It erodes atmospheres, it shapes magnetospheres, it creates the auroras in our polar skies. It's the engine of space weather, storms that can knock out satellites and power grids on Earth. All of this understanding came because one scientist looked at a pattern everyone had seen, and he asked what invisible force was behind it. He saw the comet's tail not as a curiosity, but as a weather vane, pointing straight at the Sun's perpetual stormy breath. The solar wind shapes the sky. But there are other secrets much closer to us. Giuseppe Piazzi was a monk, a meticulous man, at an observatory in Palermo. His project was simple: to make a precise catalogue of stars. It was the first night of the 19th century, January 1st, 1801. He was noting the position of a faint star in Taurus. He came back the next night to check. And the star had moved just a little. He watched it for several nights, this point of light drifting against the fixed stars. His first thought was a comet. That was a common discovery, but comets usually move on stretched, elliptical paths. This object had a slow, almost circular orbit between Mars and Jupiter. That was intriguing. There was a pattern astronomers knew, a mathematical curiosity, the Titius-Bode law. It predicted the spacing of the planets, and it pointed to a gap. A missing world should have been orbiting right where Piazzi was looking. The astronomy world was electrified. Had he found it, the missing planet, he named it Ceres for the Roman goddess of agriculture. For a short time, the solar system had a new member, but telescopes improved, and a problem emerged. Ceres was too small, a faint dot, not a disk, and then in that same region they found another. And another, Pallas, Juno, Vesta. They started calling them asteroids, star-like. Ceres was not a lone planet. It was the first of a vast population. A celestial search had begun, not for one missing world, but for thousands of fragments. Piazzi's accidental observation during routine calibration pulled back a curtain. He revealed the asteroid belt, a vast ring of primordial rubble, the leftover building blocks of a planet that never formed. These aren't just space rocks. They are time capsules preserved from the dawn of the solar system. Studying them is like reading the first pages. They hold the raw ingredients of worlds, our own included. And they taught us a new category, something between a planet and a comet, a reminder. Sometimes the most important discoveries aren't the grand, singular worlds. They're the countless pieces of the puzzle we almost left behind. The asteroid belt was fragments, a story of something that never formed, but Vesto Slipher was looking at something complete. And what he saw didn't make sense. This was at the Lowell Observatory in Arizona around 1912. His job was simple: take the light from these spiral nebulae, these fuzzy patches, and split it into a spectrum. A kind of rainbow fingerprint. By seeing which colors were bright or dark, he could figure out what they were made of. He was a spectroscopist, a chemist for the stars. But as he measured, he saw a pattern, and it had nothing to do with composition. The dark lines in the spectra, the signatures of elements like hydrogen or calcium, they weren't in the right place. They were shifted almost always toward the red. That's the Doppler effect, like a train whistle dropping in pitch as it moves away. Light does the same. A red shift means the source is moving away. Slipher measured these shifts. The numbers were staggering. These nebulae weren't drifting, they were racing away. Hundreds of kilometers per second, unthinkable speed. He published his findings, a catalogue of velocities, but he didn't push a big theory. He was a meticulous observer. Just presenting the data, he'd accidentally gathered the first evidence that the universe was in a state of rapid, large-scale motion. His main goal was to understand what these spirals were made of. He ended up measuring how fast they were fleeing. Then, over a decade later, Edwin Hubble used a new giant telescope. He made the next critical connection. He proved these spirals weren't nebulae inside our galaxy. They were island universes, distant galaxies, and when he combined their distances with Slipher's velocity measurements, the correlation was breathtaking. The farther away a galaxy was, the faster it was receding. The universe wasn't static, it was expanding. Every galaxy rushing away from every other, like space itself was stretching. Hubble's law of cosmic expansion came from that correlation, but the raw numbers, the crucial evidence of motion, that came from Slipher's quiet, accidental work. He wasn't trying to rewrite cosmology, he was just trying to read a chemical signature, and in doing that, he gave the first hard data that the cosmos was dynamic. Alive with motion on the grandest scale, it's a lesson in scientific legacy. Sometimes the most revolutionary idea isn't in the first observation. It's in the pattern that emerges when someone else looks at the data with a different question. Slipher gave astronomy the key. He just didn't know what door it would unlock. The universe was expanding, but we didn't know how far our own star's influence went. In 1977, Voyager 1 left Earth. Its mission was a grand tour of the outer planets. Jupiter, Saturn, maybe a look at Titan. It was built to last, but its planned scientific life was years, not decades. After its last planetary encounter in 1980, it was basically a museum piece drifting out, but its instruments kept listening. Its power source, a small nuclear battery, kept going. And a small team on Earth kept checking in. For years, the data was steady. The solar wind, that stream of charged particles from the sun, was a constant hum. Then in 2012, something changed. The solar particle counts dropped, almost to zero, and at the same time, the cosmic ray readings, those high-energy particles from deep space, they surged. It was like the spacecraft had sailed out of a protective harbor and into the open ocean. The team debated. Had Voyager finally crossed the threshold? The boundary where the sun's magnetic bubble, the heliosphere, gives way to the interstellar medium. This wasn't part of the original plan. No one built a specific instrument to detect this moment. They had to piece it together from the tools they had. The consensus grew. The data was too stark. Voyager 1 had, by accident, by its incredible longevity, become humanity's first interstellar probe. It slipped past the heliosphere's edge, a boundary called the heliopause. That accidental discovery gave us the first direct measurement of our sun's cosmic neighborhood. We learned the heliosphere is a dynamic protective shield. It deflects much of the harsh radiation from the galaxy. Voyager's unplanned journey mapped the size and shape of our home star's bubble in the galactic sea. It was a triumph of robust engineering meeting patient, open-ended curiosity. A machine built for one purpose quietly achieved another, far grander one. Simply because we left the receiver on. The first probe to cross into interstellar space was a triumph of endurance, but there was another instrument much closer to home picking up a whisper. A whisper that seemed to speak of life. Mars had always been a canvas for our hopes, a world of canals of dying civilizations. By the 21st century, we knew it was a cold, dry desert. But in 2003, a team using ground-based telescopes on Earth pointed them at the red planet. They weren't looking for anything in particular, just a general survey of the Martian atmosphere, measuring its composition. They split the light into its spectrum, looking for the chemical fingerprints of gases, and there it was, a tiny, unmistakable signature, methane. On Earth, methane is interesting. Most of it is produced by living things, by microbes in wetlands, by the digestive systems of animals. It can also come from geological processes, certain kinds of rock chemistry, volcanic activity. But the key fact is this: methane is fragile. In the Martian atmosphere, sunlight and chemical reactions break it down quickly. Within a few hundred years, any methane released should be gone. To see it there in a detectable plume meant something on Mars was making it now, an active, ongoing source. It was like seeing smoke from a distant chimney. You don't know if it's from a factory or a campfire, but you know something is burning. The announcement sent a shockwave through the scientific community and the public. The word biology was whispered in every news report. Had we, completely by accident during a routine survey, found a hint that Mars was alive, the debate was immediate and fierce. One camp argued for a biological source, perhaps simple microbes deep underground, producing methane as a byproduct. The other camp pointed to geology. Mars has volcanoes, though thought to be dormant. There are processes involving water and rock that can produce methane without any life at all. This single, accidental detection changed everything. It redirected the entire strategy of Mars exploration. Billions of dollars in mission planning shifted focus. Rovers like Curiosity and Perseverance were given instruments specifically designed to sniff out organic molecules and analyze methane with incredible precision. Orbiters began mapping methane plumes from space, trying to trace them to their source. The story, though, took a twist. Follow-up measurements have been frustratingly inconsistent. Some missions have detected methane spikes. Others, at the same time and place, have found nothing. The signal comes and goes. This conflict isn't a failure of science. It's science in action. It tells us the methane story on Mars is complex. It might be released in sporadic bursts from sealed underground reservoirs. It might be destroyed faster than we think in certain local conditions. But the legacy of that first accidental detection is permanent. It proved that a single, anomalous reading could capture the world's imagination and force us to ask the biggest question of all. Are we alone? Even if the final answer is a geological one, the search it sparked has deepened our understanding of Mars more than any planned experiment could have. We went from seeing a dead rock to investigating an active, chemically complex world. All because someone noticed a tiny spike on a graph where they didn't expect to find one. Methane on Mars, it suggested something was happening there we couldn't see, but the universe has these ways of bending reality itself to show us what's hidden. It was 1919. A war had just ended. A British astronomer, Arthur Eddington, he led two teams to opposite sides of the world, one to an island off Africa, the other to Brazil. Their goal was audacious. They wanted to use a total solar eclipse as a kind of cosmic lab. The moon would block the sun's face, and that would reveal the stars right around its dark edge. Now, Isaac Newton's gravity said starlight should travel in straight lines, but a new theory from a German physicist, Albert Einstein, predicted something strange. It said massive objects like the sun would warp the space around them. Light traveling through that warped space would follow a curved path, so the stars near the sun's edge would appear to be slightly out of place. Eddington's expedition was to measure that shift, to see if Einstein was right. The world was watching. This was a test of ideas that could redefine the universe. The teams took their photographs during the few minutes of totality. They developed the glass plates and they measured. The starlight had bent, exactly as Einstein's general relativity said it would. The news made headlines everywhere. A new theory of gravity was confirmed, but inside that result was a subtle detail almost overlooked. The bending of light wasn't just a test. It was a phenomenon, a prediction that mass could act like a lens, distorting and magnifying light from behind it. They called it gravitational lensing. At the time, it was a curious footnote, a neat side effect, a defect in the straight line path of light. For decades, it stayed a theoretical idea, a beautiful quirk of the math. Then, in the late 1970s, astronomers started seeing something strange. Twin quasars, identical in every way, impossibly close together. The leading idea was they weren't twins at all. They were a single, distant quasar, its light split and bent by the gravity of an unseen galaxy in front of it. the first strong gravitational lens had been found. And in that moment, the footnote became a tool. Astronomers realized this accident of physics was a gift, a natural telescope. A massive cluster of galaxies could warp space so dramatically it would magnify the light of galaxies far behind it, galaxies otherwise too faint to see. It let us peer deeper into the cosmos than any human-built instrument. But the lenses did more than magnify. They revealed the invisible. When astronomers mapped the distortion of background galaxies, they found the warping was often much greater than the visible mass in the foreground cluster could explain. The only answer was dark matter. The lensing effect was literally mapping the distribution of this unseen stuff. By studying how light bent, we could chart the hidden skeleton of the universe. What started as a meticulous test, a single measurement during an eclipse, it blossomed into one of cosmology's most powerful techniques. It turned a defect into a discovery engine. A side effect of proving Einstein right became our window into the deepest fields of the universe and the ghostly architecture of dark matter. Sometimes the greatest value of an experiment isn't the answer you're looking for. It's the unexpected tool it leaves in your hands. Gravity showed us the invisible, but there was another kind of lens, the human mind looking at data. Jan Oort had a simple question: where do comets come from? This was in the 1950s. He was mapping the paths of long-period comets, the ones that take thousands of years or even millions to swing by the sun. Their orbits were strange. They came from every direction, not from a flat disk like the planets, and their paths were wildly elongated, like stretched rubber bands flung from a great distance. Oort wasn't building a telescope. He was working with numbers, with orbital mechanics, and he saw a pattern in the chaos. These comets weren't just wandering in. Their orbits, when you trace them back, they all seemed to start from the same place, a vast spherical shell at the very edge of the sun's gravitational influence. So far away the sun would be just a bright star. He called it the Oort cloud. It was a stunning inference. From the paths of a few dozen icy visitors, he deduced 1 trillion frozen worlds. A spherical reservoir, primordial leftovers, a cosmic deep freeze holding the raw ingredients from the solar system's birth. This wasn't an observation. It was a prediction drawn from the silent testimony of orbital paths. The Oort cloud explained everything. It was the source for those spectacular, unpredictable comets. They get nudged by a passing star's gravity, sent plunging toward the inner solar system. Each one is a time capsule, preserved in the deep cold for 4.6 billion years. When we study a comet's nucleus, we're analyzing the pristine ice and dust, the stuff the planets formed from. Oort's discovery from a desk calculation showed the power of theoretical astronomy. He looked at the tracks left in the sky and reconstructed an entire invisible architecture. It taught us our solar system doesn't end at Neptune or even at the Kuiper belt. It extends nearly halfway to the next star, a ghostly halo of ancient ice, a reminder, sometimes to map the farthest reaches, you don't need a bigger telescope. You just need to ask the right question. Of the paths already written in the sky, a pulsar's heartbeat is the most reliable rhythm in the universe until it isn't. In 1992, Alexander Wolskson and Dale Frail were listening to one of these cosmic metronomes. It was a millisecond pulsar, PSRB 1257 + 12. Their goal was physics, to understand the extreme conditions of this stellar cinder. They measured the arrival time of each radio pulse with incredible precision. Over months, they built a map of its rhythm, and they noticed something subtle. The ticks weren't perfectly regular. They'd arrive a fraction of a second early, then a fraction late, in a repeating pattern. This wasn't random static. It was a wobble, a gravitational signature. Something was pulling on the pulsar gently, back and forth. The only thing that could cause such a clean, periodic tug was an orbiting body. They crunched the numbers. The data revealed not one wobble, but two distinct ones, then a third. They had found planets, so the first confirmed worlds beyond our solar system weren't orbiting a sun-like star. They were circling the corpse of a massive star, one that had died in a supernova. The environment was harsh, bathed in intense radiation. No one was looking for planets there. The discovery was a complete accident, a byproduct of studying stellar death. It shattered every assumption. If planets could form in the aftermath of a stellar explosion, or even survive it, then they must be everywhere. This single, anomalous timing measurement from a dead star's clock flung open the door to the search for exoplanets. It proved you didn't need to see a world to know it was there. You could just listen to the star and hear the silent planets conducting its dance. It was a quiet night in Ohio, August 15, 1977. The Big Ear radio telescope was sweeping the sky. It was a volunteer project run on a shoestring. The data printed out on these long sheets, columns of letters and numbers, just signal strength. A river of noise, and someone had to read it. Jerry Amon was a volunteer. He sat down with a stack of these pages. His job was to scan the rows, look for anything that stood out from the background hiss. And then he saw it, a sequence, 6 characters in a row. They meant a signal so strong it went off the chart. A narrowband radio burst, exactly what you might expect from a technological source. It came from the direction of Sagittarius. It lasted 72 seconds. That was exactly how long the Big Ear was pointed at that spot, and then it was gone. Amon took a red pen. He circled the sequence. In the margin, he wrote one word, "Wow." That gave it its name, the wow signal. They pointed the telescope back right away. They listened for days, then weeks, then years, that same frequency, that same point. Nothing. It never came back, a one-hit wonder, a shout in the dark that echoed once. Theories came up, maybe a secret military transmission, or a reflection from space debris, some natural event we didn't understand, but every explanation had a problem. The signal's characteristics were too perfect. They seemed too artificial, but it was so fleeting, impossible to verify, so it sits in this strange place. It's our best candidate for an alien signal, and we can never confirm it, but the power of it isn't in an answer. It's in the moment it was found. It wasn't found by a sophisticated computer. It was found by a human eye, a human brain looking at a paper printout. A volunteer doing this patient work saw a pattern in the noise, his instinct, his wow that captured the thrill. It shows the role of chance in science and human intuition. The universe might not announce itself with a siren. It might just leave a faint mark on a data sheet. A mark that only means something if someone is there to see it and to wonder. That red circle reminds us, in all the static of space, the most important instrument is still a curious mind. The next great surprise might be waiting, not in some AI analysis, but in the quiet moment someone looks at the data and says, "What is that?" Pluto was always a mystery. Discovered in 1930, it was small, its orbit was tilted and strange. It didn't match the other outer planets. For decades, it was just the 9th planet, a misfit out on the edge. But some astronomers looked at that odd orbit and wondered, could Pluto really be alone out there? Kenneth Edgeworth wondered. Later, Gerard Kuiper. They speculated about a disk of icy leftovers, a huge reservoir of small bodies from the solar system's formation, orbiting beyond Neptune. It was a compelling idea, a theoretical answer to Pluto's strangeness, but for 50 years it was only a theory. No one had the tools, or maybe the patience, to look for these faint, slow specks in all that dark. That changed in the late 1980s. 2 astronomers, David Jewett and Jane Liu, decided to search. It was a daunting project, a tedious one. They would point their telescope at a patch of sky, take 3 photos over several nights, and then compare them. They were looking for one thing, a dot that moved against the stars, a dot moving so slowly it could only be very, very far away, past Neptune. Night after night, month after month, they found nothing. Just empty fields. It was like looking for a single snowflake in a blizzard. Then, in 1992, after years, they saw it. On their image plates, a faint point of light had shifted. It was incredibly dim. It crawled. They had found their first object. They named it 1992 QB1. This was the confirmation. The Kuiper belt was real. Their systematic survey had paid off. It paid off almost by accident. They found something sooner than the most optimistic models predicted. The sky beyond Neptune wasn't empty. It was teeming. The discovery was a quiet revolution. Pluto was instantly recontextualized. It wasn't a solitary oddball planet anymore. It was the king of a vast, icy realm. The largest known member of the Kuiper belt. This changed how we saw the solar system's architecture. We realized the outer solar system had structure, distinct zones. The rocky inner planets, the asteroid belt, the gas giants, and now this sprawling disk of icy worlds. This population of small bodies became the source for short-period comets. That solved another mystery, but the most profound consequence was still to come. As more Kuiper belt objects were found, some rivaling Pluto in size, astronomers faced a difficult question. If Pluto is a planet, then what about these other large, round bodies in similar orbits? The definition of a planet, something we thought was settled, suddenly seemed fuzzy. This led directly to the International Astronomical Union's decision in 2006 to create a new category, dwarf planets. Pluto was reclassified. It sparked public debate, but it was a change born from evidence. From the accidental discovery during a targeted survey of countless small, icy worlds, worlds that forced us to redraw our maps, to rethink our categories. The universe, it seems, is always more populous, more nuanced than our labels can contain. Pluto got redefined because we found its neighbors, but the most energetic particles in the universe, we found those by going up. Victor Hess, he was trying to solve a mystery on the ground. This was 1912. Scientists knew the air was slightly conductive. Electroscopes, they're simple devices that measure electric charge. They would slowly discharge even in a sealed container. The leading theory was radiation from radioactive elements in the Earth's crust, that it was ionizing the air, making it conductive. If that was true, then as you went higher up, away from the ground, this effect should get weaker. The electroscope should discharge more slowly. Hess decided to test it. He took his instruments into a hot air balloon. He made a series of ascents, day and night, going higher than 5 kilometers. He was meticulous, recording the discharge rate at different altitudes, and his data told a story he didn't expect. At first, the discharge rate decreased, just as predicted. But then, after about 1 kilometer up, it began to increase, and it kept increasing the higher he went. At his maximum altitude, the ionization was several times stronger than at the surface. This was the opposite of what should have happened. The source of this penetrating radiation wasn't below him in the ground, it was above him from space. He had discovered that Earth is under a constant, invisible rain, a shower of high-energy particles from beyond our world. He called them Herrenstrahlung, radiation from the heights. We know them as cosmic rays. His balloon experiment, designed to measure a terrestrial phenomenon, it accidentally opened a window to astrophysics. These aren't rays of light. They are mostly atomic nuclei, protons, and helium nuclei accelerated to nearly the speed of light by some of the most violent events. Supernova explosions, active galactic nuclei, the turbulent magnetic fields of interstellar space. Hess's discovery connected our atmosphere to the galaxy's fury. We now know these particles are a form of natural radiation, a background hum of energy that influences cloud formation and even plays a role in genetic mutations over long timescales. More importantly, they became a new way to study the universe. We can't see the accelerators that create them directly, but by catching their products here on Earth, we can infer the immense forces at work millions of light years away. A simple instrument in a balloon basket proved the universe is not a silent, empty theater. It is an active, stormy sea, and we are constantly bathed in the spray from its most distant shores. Aristotle's heavens were perfect, they were unchanging. That idea lasted for almost 2,000 years. The stars were fixed points, eternal light, until a minister, David Fabricius, noticed something wrong. This was 1596. He was watching the sky, he knew the constellations, and one night in Cetus he saw a star that shouldn't have been there, not one that bright. Omicron Ceti, he recorded it. He thought it was a nova, a new star. These were rare, but they happened. Temporary disruptions in the perfect sphere. He watched it fade over the next months. Then he forgot about it. Years later, in 1609, he saw it again. The same star, the same place, shining brightly. That was impossible. A nova was a one-time event. A star couldn't die and come back. This wasn't a disruption. This was a pattern, a cycle. With other observers, they realized Omicron Ceti faded and came back. Roughly every 11 months, he named it Mira, the wonderful, the first recognized variable star. Its light wasn't constant, it pulsed like a slow cosmic breath. That observation, just noting an inconsistency, cracked the foundation. Stars could change, they could have lives, rhythms, processes. They weren't static ornaments. They were dynamic. Mira's discovery was an accident. It came from patient familiarity. Fabricius wasn't searching for variables, he was just watching. He trusted his memory of what the sky should look like, his willingness to note the anomaly, and then to connect two observations 13 years apart opened a new field. Soon other variables were found. Some, like Cepheid variables, had pulses so regular and tied to their true brightness that they became yardsticks. By measuring the pulse rate, you could find their true luminosity and their distance. These accidental lighthouses, found because one star didn't behave, let us map the scale of our galaxy. And beyond, the heavens were no longer a silent, perfect dome. They were a living, breathing, ticking mechanism, and the first hint of that life was a single point of light. That dared to flicker. The sky had its own maps, long before ours were drawn. For thousands of years, people in the southern hemisphere looked up and saw these two patches of light. Not stars, these soft, glowing clouds anchored near the south celestial pole. They were part of the stories, part of navigation, part of the night itself for cultures across continents. But for astronomers in Europe looking from the north, these clouds were unknown, a blank space on their charts that changed not with a telescope, it changed with a ship's log. In the early 1500s, Ferdinand Magellan set out, a voyage to find a western route to the Spice Islands, a mission of commerce and empire, and with him was a scholar, Antonio Pigafetta. His job was to keep a record. As the fleet sailed into southern waters, far from any familiar star, Pigafetta looked up. He saw the clouds. He noted them in his chronicle. Described them as nebulous, permanent fixtures in the southern sky. He called them the Cape Clouds. They were landmarks, like strange, stationary islands in a sea of stars. Useful for navigation, this was an incidental observation, a note in the margin of a document focused on winds and currents and trade. But that simple notation from a voyage for earthly gain, it brought these objects into the scientific consciousness of the West. They became known as the Magellanic Clouds, and for centuries they were curiosities, just fuzzy patches in telescopes. It wasn't until the 20th century that their true nature was revealed. They weren't clouds inside our own galaxy. They were separate, dwarf galaxies, our nearest galactic neighbors, bound to the Milky Way in a slow, cosmic dance. That accidental discovery from a ship's deck gave astronomers a gift, a close-up view of entire galaxies. Studying the large and small Magellanic Clouds became a masterclass in galactic structure. Here were stellar nurseries, aging star clusters, the aftermath of supernova, all close enough to see individual stars. They became natural laboratories. Observations of variable stars inside them, especially Cepheids, helped calibrate the cosmic distance scale, made it far more precise, and their distorted shapes, evidence of gravitational interactions with our Milky Way, taught us how galaxies evolve. How they merge over billions of years. They showed us our galaxy isn't an isolated island. It's part of a small, interacting family, the local group. All of that understanding traces back to a sailor's notation. A man on a wooden ship looking up from a roiling ocean saw something wondrous and wrote it down. He wasn't an astronomer, he was a witness, and in doing that he connected two worlds, the age-old knowledge of southern skies with the burgeoning science of the north. Turning celestial landmarks into cosmic gateways, X-rays mean violence. Back in 1964, a team sent up a small rocket. They weren't looking for black holes. They wanted to study the moon. They were checking if solar wind hitting the surface would make it give off X-rays. The rocket had a simple Geiger counter just pointed at the sky. It was a short flight, only a few minutes above the atmosphere, but in that little window the instrument caught something unexpected. It wasn't coming from the moon. It was from a fixed spot in the constellation Cygnus, a source of X-rays so strong it flooded their detectors. They called it Cygnus X1. It was a mystery. This brilliant, flickering beacon in a part of the spectrum we can't see. What could be that hot, that energetic, and change that fast? The answers started to take shape when optical astronomers looked at that same patch of sky. They found a star, a blue supergiant, massive and bright, spinning through space, but its motion was odd. It wasn't going in a straight line, it was wobbling. Like it was locked in a tight, furious dance with something invisible. By measuring that wobble, they could figure out the mass of whatever was pulling on it. The numbers were staggering. The unseen thing had to be at least 10 times the mass of our Sun. And yet it gave off no light, nothing, a 10 solar mass ghost. At that size, the known laws of physics only left one possibility. The gravity would be so strong that not even light could get out. It had to be a black hole. That accidental find from a rocket experiment changed everything. Black holes had been a mathematical prediction for decades. A curious, maybe theoretical endpoint of Einstein's equations. Cygnus X1 turned that theory into something tangible, something violent. Here was a binary system, a cosmic vampire. The supergiant star pours its material toward the black hole. That gas doesn't fall in quietly. It spirals into a superheated disk, a maelstrom of friction and magnetic fields so intense it glows with X-rays. The flicker the rocket detected, that was the death scream of matter crossing the point of no return. That one unintended measurement gave astronomers their first real target, a laboratory for studying the most extreme gravity in the universe. It proved the monsters weren't just in the equations. They were out there, hidden in plain sight, revealed only by the high energy cries of the stuff they eat. The black hole's X-ray scream was a beacon of cosmic violence. But there's also a place of perfect celestial stillness, a place where gravity and motion cancel each other out. The Lagrange points. In 1906, Max Wolf was at his telescope. He was pioneering a new technique. He wasn't just looking, he was taking photographs of the same patch of sky over several nights. Then he'd compare the plates. Looking for a dot that moved against the fixed stars, he was hunting asteroids and he found one. He named it Achilles, but its position was the real story. It wasn't in the main asteroid belt between Mars and Jupiter. It was far ahead of Jupiter, in the giant planet's own orbit. It was locked in a gravitational sweet spot. A Lagrange point, specifically the L4 point, 60 degrees ahead of Jupiter. In that region, the gravitational pull of the Sun and Jupiter balances perfectly with the orbital motion. An object placed there can stay there, essentially forever, in a stable triangular dance with the two massive bodies. Wolf's discovery was an accident of his systematic survey. He wasn't looking for objects at Lagrange points. The theory of these points had been worked out by mathematicians over a century before, but no one had found a real object residing in one. Achilles was the first proof that these theoretical havens were actually occupied, and it opened the door. Soon, more asteroids were found at that same point. Then another cluster was discovered, 60 degrees behind Jupiter at the L5 point. They were named the Trojan asteroids after heroes from the Iliad. These weren't random wanderers, they were a vast population, perhaps as numerous as the main asteroid belt, all trapped in gravitational harmony with the solar system's largest planet. This accidental discovery revealed a new architectural feature of our solar system. The Trojans are primordial time capsules. They've been co-orbiting with Jupiter for billions of years. Preserved in those stable points, studying their composition tells us about the raw materials that were present in Jupiter's region when it formed, but their existence also holds clues to the planet's own history. The fact that so many objects are trapped there suggests Jupiter didn't form in its current position. It likely migrated inward early in the solar system's life. Sweeping up and capturing this cloud of debris in its gravitational wake, so these quiet, stable points are a record of a violent, mobile past. They are a natural laboratory. Not just for the early solar system, but for celestial mechanics itself. The Trojans show us that stability in the cosmos isn't always about standing still. Sometimes it's about finding the perfect rhythm within a grand, orbital dance. And sometimes that perfect rhythm is discovered by a patient astronomer. Comparing photographic plates who simply notices one dot where no one expected it to be. They were looking for moving dots and they found that rhythm, the dance of the planets. But then there was another rhythm, a human one, that changed everything. It was lunchtime. A radar engineer in the 40s was on a break. He was watching a test signal. And he noticed something. The microwaves he was working with, they passed through the atmosphere with surprising ease. There was a specific band of frequencies where the air, with all its water vapor and oxygen, it became almost transparent. It was a quiet window in the noisy spectrum of the sky. This wasn't a planned discovery. It was an observation from a wartime project focused on radar, on detection and communication. They'd found a clear channel, a slice of the radio spectrum where signals could travel to space and back with very little interference. This finding, this microwave window, it landed on the desk of a writer. Arthur C. Clarke. In 1945, he published a paper not about radar but about the future. He proposed an idea. If you placed a satellite in an orbit that matched Earth's rotation exactly, it would appear to hang motionless. A geostationary satellite, and if you used those specific microwave frequencies, you could bounce signals off it. You could link continents. That quiet window the engineer noticed over lunch, it made Clarke's vision practical. It was the perfect marriage, a theoretical orbit meeting a serendipitous band of clear air, and together they birthed the modern communications satellite. The entire architecture of our global village television, international calls, live news, it rests on that foundation, but the story doesn't end there. That same clear window, that slice of quiet sky, it became a gift to astronomy. Radio astronomers realized they could point their dishes upward, tune to frequencies within that window, and listen. Listen to the universe with a new clarity. The faint whispers from distant galaxies, the cold glow of interstellar gas, the pulse of dying stars, it all came through with less static from our own atmosphere. A solution crafted for earthly communication had accidentally optimized our ears for the cosmos. It reminds you that the line between invention and discovery is blurred. An engineer solving a practical problem for defense inadvertently handed astronomers a key to a quieter channel, a channel through which the universe speaks more clearly. Progress isn't always a straight line from question to answer. Sometimes it's a side effect, a solution for one mystery unlocking the door to 1,000 others. That clear channel made the sky quieter, but then you had objects too dim to really make any noise. They were called failed stars. For decades, they were just a theory. A missing link, something with more mass than a planet like Jupiter, but not enough mass to start that sustained nuclear fusion, the thing that makes a star shine. They'd just be warm, cooling embers. Astronomers called them brown dwarfs, and for years they were ghosts. Every candidate turned out to be something else. A low-mass star, something different. The search went on and on. Then, in 1995, a team was testing a new technology, adaptive optics. It corrected the blur from Earth's atmosphere in real time. They pointed it at a nearby star, Gliese 229a. It was just a calibration target, testing how sharp the instrument was, and in those new, crisp images they saw it. A faint reddish dot clinging close to the star, a companion. At first glance it could have been a background star or a distant planet, but they took its spectrum. They split the light into a chemical fingerprint, and there it was, methane. That was the key. Methane forms where it's cold. Stars are too hot for methane to exist in their atmospheres. Only in cool, dense atmospheres, like a giant planet or something even cooler. That's where you see methane bands that strong. The temperature and mass from the data put it right in that theoretical gap. Too cool to be a star, too massive to be a planet. They had found it, Gliese 229b, the first confirmed brown dwarf. They weren't on a dedicated hunt that night. They were just trying out a new camera. But because they looked and because they recognized what they were seeing, a mystery that lasted decades was solved. This accidental discovery did more than check a box. It showed a whole hidden population. These dim, warm objects, we now know they're incredibly common. They fill that gap between stars and planets, a whole class of objects that had been hiding in plain sight, often looking like faint stars in older surveys. They taught us that star formation makes a full spectrum of objects, not just the brilliant successes. Some cosmic furnaces just never get hot enough to light. And in their quiet, warm gloom, they hold clues about that blurry line between a star and a planet and how both of them come to be. We thought the cosmic microwave background would be perfectly still. A uniform afterglow from the beginning, but in the 70s measurements got better and they found a flaw, a dipole. One half of the sky was just a bit warmer than the other half. The simple answer was motion, our galaxy moving through that ancient light, a headlight effect, but the speed was the shock. The Milky Way wasn't drifting. It was racing over 600 kilometers per second. And it was heading somewhere toward a point in the sky near Centaurus and Hydra. This wasn't random drift. It was a flow. Something huge was pulling us, pulling thousands of other galaxies too. A river of motion. They called it the Great Attractor, an accidental find. Just from trying to clean up a small imperfection in the universe's first light, you couldn't see it with optical telescopes. It was hidden behind the plane of our own galaxy. In the zone of avoidance, dust and stars in the way, but its gravity was unmistakable, a colossal mass, maybe 100,000 times the mass of our galaxy. A gravitational anchor for our whole local supercluster. The realization was deep. We're not floating in a static cosmos, we're part of a grand choreography. The Milky Way, Andromeda, all our neighbors, being drawn toward this hidden focal point. It showed the sheer scale of cosmic structure. Galaxies aren't scattered randomly. They form a vast web, great walls and filaments, immense voids. The Great Attractor sits at a node in that web. Its pull is a direct testament to dark matter, the unseen scaffolding that dictates how galaxies flow across billions of light years, trying to understand a tiny temperature difference in the oldest light. It accidentally mapped a river of galaxies, all flowing toward a hidden giant. It showed that even our motion on the grandest scale isn't our own. We're caught in a current, pulled by the invisible architecture of the cosmos. Richard Carrington was in his observatory. It was September 1st, 1859. He was drawing, mapping the dark spots on the sun. He projected the image onto a screen, tracing the shapes. He was an amateur, but he was careful. And then, at 11:18, something happened. Two patches of white light, blinding light, they burst from a group of sunspots, so bright he thought his screen was flawed. He went to get someone, a witness. But when he came back, the light was gone. He had seen a solar flare, a catastrophic release of energy on the sun. He didn't know what it meant, but the consequences were already coming. Hours later, a torrent of particles hit Earth, a coronal mass ejection. It slammed into our magnetic field, and the night sky erupted, auroras from the poles to the tropics. Crimson and green, so bright that in Cuba, people read newspapers by the light. In New England, they thought a city was on fire, but the real wonder was in the telegraph offices. The lines went wild. Operators found they could send messages with the batteries disconnected. The induced currents were that powerful. Sparks flew from the equipment. Some telegraph papers caught fire. That was the Carrington event, the most powerful solar storm we know of, and it was seen by accident, by a man making a sketch. His observation gave us the first direct link, cause and effect written across the sky, and in the sparks from our machines, that one flash founded a field of science. Space weather, we learned the sun isn't a placid lamp, it's a stormy sphere. Its moods reach across 93 million miles. To touch our world today, a storm like that would be a crisis. A global technological crisis. It could knock out satellites, disrupt power grids for months, cripple communications. Carrington's sketch is a reminder. Our civilization lives within the atmosphere of an active star. We are connected to its tantrums more than we knew, and sometimes the most important warning doesn't come from a sensor. It comes from a curious hand, a pencil on paper, at just the right moment. A solar flare was a local warning, but the sky had travelers from much farther away. Astronomers had theorized for decades, small objects, rocks and ice, ejected from other stars. They should be drifting through the galaxy, passing through ours sometimes. But no one had ever seen one. The solar system felt like a closed family. Then, on October 19, 2017, a telescope in Hawaii blinked, the Pan-STARRS survey. Its job was planetary defense, a nightly scan for faint streaks, asteroids that might be on a path to Earth, a routine watch for local threats, and that night its software flagged a dot. A very fast dot. It was already moving away from the sun. The initial calculation was startling. Its orbit wasn't elliptical, not a closed loop. It was hyperbolic. An open curve. This object wasn't from here. It was just passing through. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar. The first confirmed interstellar visitor. Its discovery was a complete accident of purpose. The telescope was built to find things that belong to us, things that could hit us. And it found something that didn't belong to us at all, something just dropping in. The data was strange. It showed no coma, that fuzzy cloud of gas and dust around a comet. So it was rocky or metallic, and its brightness varied dramatically as it tumbled. That meant its shape was extreme, long and thin like a cigar or a pancake. An object unlike any we'd seen in our own system. Here was a physical piece of another star system, a sample delivered to our doorstep. We couldn't chase it. It was already leaving at a blistering speed, but for a few weeks, every telescope we had turned to look, we gathered every photon we could. That brief visit raised profound questions. Where did it come from? What system ejected it, and when? Its unusual shape sparked debate. Could it be artificial, a fragment of some ancient technology? Most scientists think not. The likely explanation is natural. Maybe a shard from a planetary collision long ago in a system far away, or a peculiar icy object with a hardened crust that hid its cometary nature. But its existence changed our perspective. It proved the galaxy isn't static. It's a dynamic exchange. Star systems fling material out into the void. And that material drifts for eons until it briefly lights up in someone else's sky. We are not isolated. We're part of a grand material conversation between stars. All the rocky planets, the asteroids, the comets here, they formed from a local cloud. Oumuamua was proof that other clouds make other things, and sometimes those things cross the immense dark to say hello. The next time Pan-STARRS or another survey catches a faint, speeding dot, we'll look with new eyes, not just as a potential threat, but as a potential messenger. A piece of a distant story written in rock and ice, sailing silently through the night. The first interstellar visitor was silent, then came the next signal. It was a tremor in spacetime. LIGO and Virgo picked it up in August 2017. A chirp, a rising tone that ended in a crash, but this one lasted nearly 100 seconds. That was much longer than the black hole mergers. The data was clear. This wasn't two black holes, this was two neutron stars, the ultra-dense cores of dead suns. And this signal had a location, a rough patch of sky. Automated alerts went out immediately. Observatories across the planet got the call. This was the moment. The chance to hear something and then look. What followed was a global scramble, a coordinated reflex. Telescopes everywhere on the ground and in space turned toward that one point. They were looking for a flash of light, something to match the gravity ripple, and they found it in a galaxy called NGC 4993, 130 million light-years away. A new point of light appeared. It wasn't a supernova, it was something rarer, a kilonova. The explosive aftermath of two neutron stars colliding. For days it blazed. In ultraviolet, optical, infrared light, space observatories caught a gamma-ray burst too. Just seconds after the gravitational wave arrived, the universe had sent the same message in two different languages. And we were listening in both. The data from that event was a treasure trove. The light's signature held chemical fingerprints, newly forged elements. That was the accidental bonus. The cosmic alchemy was real. The violent merger cooked up staggering amounts of heavy elements, gold, platinum, uranium. In that one flash, a decades-old mystery was solved. We finally knew the universe's store of these heavy atoms. They didn't come from supernova. They came from the catastrophic collisions of stellar corpses. The gold in a wedding ring, the platinum in a catalyst, that was once stardust forged in a kilonova's fury. That single alert and the global response it triggered, it didn't just solve one puzzle. It opened a new window on the cosmos, the official birth of multi-messenger astronomy. We no longer had to just see the universe or just hear it. We could do both at once. Cross-referencing the stories told by light, gravity, particles, it turned a theoretical strategy into an operational reality, all because two dead stars, locked in a final embrace, sent out a ripple. And an entire planet of watchers was ready, by chance and by design, to catch the echo and witness the glow. The gold in that ring came from a star collision. But the actual scale of things, the number of galaxies, we couldn't really see it. Not until 1995. The Hubble telescope had a problem then. It was fixed, the Mira was corrected. It was working fine, but it wasn't being used much. The director at the time, Robert Williams, he had a special privilege, some directors' time. He could point Hubble anywhere for a long exposure without asking anyone. He decided to take a risk. He picked a target that looked like nothing, a tiny dark spot near the Big Dipper. No bright stars there, no known galaxies. Just black. To a lot of astronomers, it seemed like a waste. Hubble time was the most valuable thing. Using 10 days, 300 orbits to stare at emptiness, that sounded like career suicide. But Williams and his team went ahead. They wanted to look past the nearby stuff, the obvious stuff, to take a core sample of the universe. For 10 days, Hubble collected light. Photon by photon, the data built up, and when they finally processed the image, the room went quiet. That black patch wasn't empty, it was full, a tapestry of light. Thousands of galaxies, each one a smudge, a swirl, a streak. They weren't all the same. Some were spirals like our own, others were fragments colliding. And the faintest ones, the reddest smudges, those were the deepest. Galaxies seen when the universe was very young. The Hubble Deep Field wasn't a picture of known things. It was a revelation of what was hidden. That one image from a pinprick of sky had maybe 3,000 galaxies in it. It gave a visual answer to an old question. How vast is it? The answer was humbling. If every patch of sky had that many, then the total wasn't billions of galaxies. It was hundreds of billions. Earth's place got smaller again, but more than numbers, the deep field showed evolution. By looking far away, which is looking back in time, you could see galaxies young. You could see how small blobs merged into the big structures we see nearby. It was a family album for the cosmos. Those so-called wasted orbits became one of the most important observations ever. It changed how people saw the universe. It gave a feeling of depth, a visceral understanding that no graph could give. It proved something about exploration. The greatest treasures aren't found where the light is bright. They're found by having the courage to stare into the void, to trust that if you gather enough faint whispers, they'll become a roar. The universe, it seems, has no truly empty spaces, only depths we haven't had the patience or the bravery to measure. That single patch of sky, it looked empty. But it was filled with galaxies. It shows what you can find if you're patient, if you're willing to look at nothing. And that's the final lesson from these stories. They aren't just a string of lucky breaks, they're a pattern, a blueprint for how science really moves forward. Each accident sent out a ripple, and those ripples, they didn't just add a footnote to a textbook. They redirected whole rivers of research funding. They inspired new technologies. More than anything, they trained generations of scientists to see the anomaly not as a nuisance but as a signal. A tap on the shoulder from the cosmos. Take the cosmic microwave background, that frustrating hiss. It didn't just confirm the Big Bang. It birthed the entire field of precision cosmology. It drove the design of satellites like Kobe and Planck, instruments built with one goal: to listen more carefully to that ancient whisper or gravitational waves. The first detection wasn't a targeted look at a specific star. It came from building an instrument so sensitive it could hear the universe ring like a bell. LIGO was built on the chance that something someday might make it chime. That's science betting on serendipity. Modern astronomy has learned to build chance into its architecture. We don't just rely on lone observers anymore, though that's still vital. Now we cast wide nets. Projects like the Vera C. Rubin Observatory will scan the entire visible sky every few nights. Not to test one theory, but to create a living movie of the cosmos. Its purpose is to find what changes, to welcome the unexpected flash, the moving dot, the star that shouldn't be there. That's a systematic embrace of accident. Open data policies amplify this. When one team's anomaly is published for the world, a researcher on the other side of the planet might see it as the key to their own puzzle. The digital sky becomes a shared workshop. This leads to a deeper question. With limited time and resources, should we allocate them for pure, curiosity-driven exploration? For staring at an empty patch of sky for 10 days with no guarantee, the legacy of every story we've shared says yes. The greatest returns have consistently come from the questions we didn't know to ask. From instruments built for one purpose that revealed something utterly different. This isn't about wasting resources, it's about investing in our own humility. It's a bet that the universe is more imaginative than we are. The ethical imperative is clear. To solve tomorrow's challenges, understanding climate, finding new resources, ensuring our survival, we need the fundamental knowledge that only open-ended exploration provides. The GPS in your phone works because we understood general relativity, a theory born from a man thinking about falling elevators and bending starlight. The connection is never direct, but it's inevitable. By chasing the faint hiss, the wobbly star, the misplaced dot, we build the foundational understanding from which all applied science grows. So the task for the next generation isn't to avoid accidents, but to cultivate them, to design tools sensitive enough to catch the universe's whispers, to foster a culture where a graduate student feels empowered to say, "This scruff on the chart is interesting," to maintain protected spaces in our budgets and in our minds for the pure joy of not knowing. The history of astronomy is a chronicle of beautiful mistakes. Our future depends on our courage to make more of them, to remain open always to the universe's surprising gifts. Because the next great discovery isn't on our map, it's waiting in the static, in the glitch, in the quiet courage to point a telescope at the dark and see what shines back. It started with a broken lens and a faint, steady glow, and it ends with a universe that's completely different now, not a silent, static dome anymore. A dynamic place, a whispering place, endlessly surprising. We've gone through 30 stories, 30 beautiful mistakes, from the hiss that was the birth cry of everything, to the ticking heart of a dead star, from the hidden planet to the invisible ocean of dark matter. Each one began with a question mark, not a grand plan. A moment where someone decided to listen to the static, instead of trying to silence it. That's the real map of how we understand things. It's not a straight line from an idea to proof. It's a sprawling, branching tree, and the most fruitful limbs grew from a crack in the path everyone expected. Science, the living part of it, isn't a collection of facts. It's a process, persistent, humble inquiry. It's the willingness to be wrong, to be confused, and to follow that confusion wherever it goes. So often, the right answer has been waiting, just off the well-lit road, in the shadows of a wrong turn. These stories are a masterclass in humility. They remind us, forcefully, that the universe works on a scale of imagination. A scale that dwarfs our own. Our best-laid plans, our most elegant theories, they're just sketches. The cosmos holds the final draft, and it's always ready to surprise us. That's not a failure of our intellect. It's the condition, the very condition of discovery. Our instruments, our questions, they're probes we send into the dark. We can't predict everything they'll touch, so what do we take from that? A sense of wonder, sure, but also a call to cultivate a certain kind of attention, to value the anomaly as much as the confirmation, to build tools sensitive to whispers, not just shouts, and to protect the space in our institutions. In our own minds, protect the space for pure, open-ended curiosity, for the courage to point a telescope at an empty patch of sky and wait. When you look up at the night sky, remember that the next great revelation, the one that rewrites the textbooks again, it might not come from a perfect billion-dollar mission. It might be hiding in a glitch. A glitch in a satellite's data, in a graduate student's note about a strange squiggle on a chart, in the quiet persistence of an amateur astronomer on a cold night. The universe is still speaking in riddles. Our task is to stay curious enough, humble enough to listen.